Okay, the recordings should be started. Yeah, great. Okay, then let me jump into the content directly. So for those of you who are not yet aware of the INCREASE project, I will just briefly give an overview of what it is about. So basically, in the INCREASE project, we are tackling with the centering around 5 business cases, several challenges that we're currently facing in applying recyclates in high and added value products. And we are looking into producing recyclates and also applying those in the business cases. So we have 5 business cases, as I mentioned. And first of all, we are looking into food contact material. So there we're tackling challenges that are currently persisting in terms of regulation, looking into those. So for example, for food contact material, currently it's only possible to use material that is coming from closed loop from food contact to food contact again. And this is something that we're investigating here. And also the fact that in our high or added value application, we are looking for material that is also generally must be quite specific because it needs to endure quite some high temperatures and also have some steam tolerances. So we are here looking into the Varoma device, which is from Vorwerk. Then second of all, also another challenge that is quite known in the electrical and electronic equipment world, let's say, is the flame retardancy. So here we are working with an EV charger where we're looking for the recyclates that can be then applied. And the challenge is, of course, also the additives that are then causing partly some troubles in the recycling system. The third business case centers around chemical resistance. So here we have a home composting device where we are looking for recyclates that can endure the chemicals, and also, for example, with the leachate that is produced in this home composting device to ensure that no contamination is then migrating into the leachate. Then we are tackling also ESD material, so electrostatic discharge material, in terms of these products that you can see, these pallets, which are used to transport automotive components, for example. And this material needs to be of high quality and also have this ESD property, and endure also several different mechanical tests. And last but not least, we have medical equipment. In this case, we have the electrical toothbrush from Philips, which of course has also certain legal restrictions in terms of traceability of the material. Also, contamination needs to be 100% safe, so that it can be also used in contact with skin, for example. So these are the 5 business cases that we're tackling in the project, and these are all each representing one specific challenge that the sector is facing in terms of applying and recycling the materials. And we are looking into technical aspects, as I've just mentioned. So we are looking into materials that we can technically then recycle with different recycling technologies into available recyclates, and then applying those also. But we are also looking beyond technical aspects. So we are really investigating the entire value chain. We're looking into regulatory restrictions, as I've just mentioned, which are partly challenging for these applications. But we're also looking into how can we build acceptance among consumers, and how can we also ensure that consumers, for example, dispose of the products correctly so that they then enter also the recycling stream. And we're also looking at the entire system, so really taking the system perspective and identifying where are the levers that we can intervene in order to also improve the system and make it functional in order to be fully circular. And today we will be focusing also on the environmental and costing aspects that we are assessing in the course of the project. And therefore, I would like to just briefly mention, you are most certainly all aware of the different R strategies that are possible to keep products and materials in the loop. First of all, of course, repair and reuse needs to be targeted in order to keep the products in the cycle. But in the INCREASE project specifically, because every product will become waste and it reach its end of life at some point, we are then looking into how can we keep the materials in the loop. And there we are specifically looking into 3 technologies, which is mechanical recycling, solvent-based recycling, and pyrolysis, which is one of the chemical recycling pathways. And there is also another crash course upcoming next week. Actually, it got postponed to next week, where we will be deep diving also into those 3 recycling technologies. So if you're interested in that, please make sure to join us next week as well. And here I would like to just show you that for the different business cases, as I've mentioned, we are looking into different materials, in different feedstocks, basically, where we are trying to identify which product categories in the e-waste stream are suitable in order to then achieve the material properties that are needed to apply those recyclates in the different products, and also finding strategies in terms of which recycling technology is most suitable. And in the next about half an hour, we will dive into several aspects of this. So first of all, I will start off with the life cycle assessment that we at Fraunhofer IZM are conducting, and we are focusing specifically on the first stages that you can see. I mean, it's in general a cycle, but the first ones that you can see here on the screen. So from the collection of the waste material to processing, sorting, recycling, and essentially then also compounding for the material then to be reused in new products or reapplied. And this is also the same focus for the life cycle costing that David will then follow up on. And last but not least, Rucha will focus on further steps in this value chain with her framework, starting from the compounding stage. And of course, with every new technology that is out there, it is crucial to first understand what are the implications in terms of environmental implications, but also in terms of costing to get the economics right. But we will first dive into the environmental assessment. And first of all, I always like to point out the following challenges that are generally applicable to life cycle assessment of recycling, in our case specifically e-waste plastic recycling. And this you can take this as a general disclaimer to all the carbon footprints that are out there, because one needs to always fully understand what was being assessed and how was it assessed. And this is particularly important due to several reasons, because first of all, we are dealing here with a multifunctionality system. So inherently to the recycling system is this multifunctionality that on the one hand, it produces new materials, and on the other hand, it treats waste. So we have a dual purpose, let's say, of the system itself. And second of all, particularly for e-waste, we are dealing with a lot of different co-products. So we have metals, of course, in the stream, and these are typically also the economic driver for the recyclers, depending, of course, on the price fluctuations of materials. But these need to also be taken into account when allocating the different environmental burdens across the different materials. And also, thanks to recycling, we can, of course, keep the materials in the loop, but this also means that we need to somehow account for the different life cycles that the material is flowing through and is being used or reused even. And at the same time, we are facing quite a lack of representative data. So therefore, we were also collecting quite a lot of primary data, which I will show just in a bit, amongst the project partners and even beyond, in order to come up with some good results and findings. And last but not least, there is always this difficulty of how to compare different life cycle assessments, because there is always different functional units and system boundaries that can be applied. So please, when interpreting numbers that you see, always try to first understand what was being assessed and how was it being assessed. And now I would like to, with this in mind, I would like to walk you through the process of a life cycle assessment, which is generally also the structure or the approach that is applied for the life cycle costing. And first of all, we are setting the goal and scope, and this is really important, as I already mentioned. Also important to report this, also and to make clear what was being looked at, because there's many influencing factors that that need to be clearly depicted. And then second of all, we are collecting all the data that is needed in order to conduct the life cycle assessment. So there we were looking into primary data and also filled wherever gaps were with secondary data, so literature data and also expert information. And then we conducted the life cycle assessment with an LCA software. And then we are interpreting and also currently documenting the results in a final publication that will be available next year. So first of all, our goal in the life cycle assessment that we are conducting is to compare these innovative recycling routes, so the different mechanical, solvent-based, and chemical recycling routes, and compare it to the primary production of the material. So if the material would be produced with fossil fuels, and also taking into account the current waste treatment system. And we are particularly focusing on the material provision perspective, because you can take those two approaches and those two perspectives, let's say, due to the fact that we have this multifunctionality of the process itself. And here we are looking into the material provision perspective for the different business cases, because essentially what we're trying to do is in INCREASE is generating new material which is of high quality and can be directly used in high added value products. And for another approach, so the waste treatment perspective, we are also taking for a combination approach that we are also testing in INCREASE, where we are trying to combine for one waste stream different recycling technologies in order to maximize the production of recyclates. And the scope that we are looking at here is, as I mentioned already, from the collection until the compounding step. So the e-waste is basically flowing through the steps until then eventually a new product can be produced out of the compounded material. So this would be the goal and scope. And as I mentioned already, we collected quite a lot of primary data and are filling the gap with secondary data that we have extensively analyzed. And now I would like to briefly mention and explain to you one example that we are doing. So for example, we are looking now into the mechanical recycling of high quality recycled polypropylene, which is derived from the toys. So colleagues identified initially that the toys fraction can be suitable to get high quality polypropylene out of it in order to then apply it in the Bokashi home composting device that I mentioned initially. And afterwards, these toys were treated separately in the mechanical recycling stream, and then it was eventually compounded, and now we're trying to also test this material in the demonstrator. And we looked basically at all the different inflows and outflows in terms of material that are flowing through the system, but also coming out of the system, such as the co-products, and also the energy and all of the other resources that are consumed during the process. And here, just some preliminary results. So we then modeled this entire process flow and calculated the environmental impacts for different impact categories with the environmental footprint 3.1 methodology by the European Commission. And then we compared it now here to the primary production of polypropylene from fossil fuels. And here you can see that, for example, in terms of climate change, mechanical recycling is significantly lower if you compare it to primary production. And I would like to also stress here that typically climate change is of most interest and has quite a widespread attention to it. So therefore, it's also more extensively researched in terms of the calculations behind and also the methodology. So might be the most reliable category that is currently out there. But also, if we look into the other environmental impact categories that you can see here, it becomes clear that mechanical recycling has significant savings potentials in several aspects. And now here you can also see the breakdown of the different processing steps. So the total impact here illustrated with 100% in gray is the full impact of mechanical recycling to this 1 kilogram of polypropylene that is being produced within the recycling system. And for all the environmental impact categories, except for water use, for example, here, the compounding step makes up the highest share because it also uses quite a lot of energy that is for heating. And the mechanical treatment step, for example, that is mainly composed of shredding, magnet separation, eddy current, and so on, makes up a significant share also in terms of the climate change. And I would like to also mention here that in order to maximize the environmental savings that we can have with recycling, we also need to look at the entire value chain. So currently of the 2.6 million tons of e-waste plastics that is generated in Europe, only 1.4 million tons are then collected. So we need to also improve this collection in order to allow also the materials to even enter the recycling system. And also if we look at the share that is then being actually recycled and treated, the recycling rate remains relatively low, so we need to work on that and also on sorting and treating the different product categories in the most beneficial way. And if we look at the recycling application rate, so the share of recyclates that are used in new products for the electrical and electronic equipment sector, it remains as low as 3.2%, which means that still about 79% are coming from primary plastics. So there we need to also ensure that we increase the quality of the recyclates so that they can be applied, and also then increase the application rate of these recyclates in order to maximize these environmental savings that we can have through recycling. And in the next steps, we will also look at solvent-based and chemical recycling, and we will also assess this recycling cascade that I mentioned initially, and also do a lot of sensitivity analysis steps and evaluate different scenarios in order to really interpret the findings well and also to get some actionable results out of it. And now I would like to hand over to David for the economic assessment.
Thank you, Teresa. So hello, welcome. I'm David. I'm a PhD candidate at ETH Zurich, and I'm gonna present to you today what we as the Group for Circular Economy have done in terms of the economic assessments of producing high-quality plastic recyclates from WEEE. So we are still on the supply side, as you can see here, supplying granulates. So I'm just, okay, nice. All right, so I'm just checking if this is, yeah, okay, awesome. So I can control the slides perfect. So we have been conducting economic assessment of 3 INCREACE closed loop WEEE to electronic products recycling chains. So 3 of the 5 that Teresa has mentioned already at the beginning. So we focused on the case of PP for chemical resistance, the PC ABS with flammability resistant, and the ABS for medical application case. To assess the economic performance of a recycling chain, there are several methods to do that, and we chose a so-called life cycle costing approach. And this life cycle costing approach is very similar to an environmental assessment, what Teresa has presented to you already, the so-called LCA. The steps are the same, but there are maybe some other aspects to reflect on and to look at. So for us, we chose 2 different perspectives. So first of all, a so-called system level LCC, where the question that we are interested in when you do this is, what are the total system costs of producing 1 ton of recycled plastics that in our case of INCREACE can substitute virgin material? And with such a system, just a perspective, you can answer or help to answer several questions. So for example, from a more like a policy perspective, you can understand better, are recycling chains economically viable? Can policy intervention potentially make this process more viable? Then related to that, you can also understand better along the value chain, where are the cost hotspots? of producing high-quality recyclates, and maybe where in this value chain does investment have to occur first. And then lastly, the system-level perspectives also allows to integrate or complement the LCA. So we can then complement the findings from Teresa, for example, that has found out that there was emission savings from mechanical recycling with the costs that these savings come about. And then we also applied a second perspective, which is a so-called actor-level LCC. The difference is here that you draw your system boundaries between the different steps of the recycling chain. So in this case, between the treatment, recycling, and potentially compounding. And the question you want to answer with this is usually, what are the minimum selling prices that actors along the recycling chain have to charge in order to break even, in order for each actor to have a viable business case? So it gets a bit more into the different business economics to understand, can each actor achieve financial viability in this entire chain? What are realistic margins that can be charged? And then maybe even more importantly, questions regarding value chain coordination. So where is the recycling chain, if it doesn't work right now, breaking down, or where are the largest profits that can be made? So this is to motivate a bit the method that we've been doing. And a second important question is also for a life cycle costing analysis is to choose the baseline and let's say the assessment case. So in our case, we wanted to look only at the incremental costs that are needed to better valorize recycled plastics, or better valorize e-plastics that are currently not recycled, and to recycle them. So what we do as a baseline is that we map the current system as it works right now, of course, very stylized. That means we look at WEEE entering from collection into a WEEE treatment facility, where then metal is recycled, but e-plastics end up as a residue for incineration. And all the virgin plastics is created from fossil resources. And we compare this with the assessment cases from the INCREACE project, where instead of incinerating e-plastics, they are further separated into the different polymer types and then can enter either solvent-based or mechanical recycling to substitute the virgin plastics in new products. So for this, we needed to gather different data sources, again, similar to Teresa, primary and secondary data sources on what changes in terms of material flow between this baseline scenario and the assessment cases, and also what changes in terms of economic flows, costs, and revenues. And we did that we are right now doing that for 3 cases, and we can give you a short teaser. We have not yet the final numbers ready, but we can give you already an example for the case of recycling ABS from copiers to medical application skin contact, the toothbrush. So in the INCREASE project, the partners have identified 3 main, let's say, changes in the current process that can help to recover ABS from copiers for toothbrush housings. And the first of these strategies is the so-called strategic pre-sorting, which means at the beginning, when copiers are entering into the material recovery facility, we can cluster them by color. So in this case, separate the white from black copiers, which allows then them to be separated later with near sorting. So near sorting can be applied to sort out white ABS, and this white ABS can then enter into solvent-based recycling, where contaminants are removed and ABS flakes are recovered. From an economic perspective and from a cost perspective, there are several trade-offs that can occur in such a recycling chain. So for the strategic pre-sorting, the main advantage is that you can achieve a white ABS outcome in the end. So you can achieve color purity, and you can even increase the sorting efficiency in the later steps of the density separation or this near sorting separation, but this comes a lot at the cost of higher manual labor when you need to actually separate out white and black parts of the copiers. This then the decision to add an additional near sorting step has definitely multiple advantages. First of all, to actually sort out ABS, but also to reduce costs of sending heavy plastics fractions to incineration. At the obvious cost of this are that you need to invest in such a near sorting machine, and also that they come with operating expenditures. And then similarly, in the last step, so we can, during solvent-based recycling, it allows to recycle so-called high-quality recycled ABS with low contaminants that can be a great revenue potential for the recycling actor. But of course, since we don't have industrial solvent-based plants running right now, or only very limited, it comes along with different investment costs and operating expenditures. In the following of the project, we will dive deeper into this and hopefully by the end come up with some estimates of how these trade-offs play out. And in addition, we also want to look at key policies and also macroeconomic factors that can in the end determine the competitiveness of plastic recyclate production routes from WEEE with virgin plastics. And for that, we also need to take into account different policies occurring right now. So for example, looking at the WEEE directive revision, it's going to be interesting to see how the collection targets evolve and how will that affect the availability of different target polymers from, for example, copiers or other sources that are rich in ABS or in other target polymers that the business cases want to recover. Then another interesting development will be to also take a look at what is happening in terms of gate fees for incineration on the inclusion of WEEE in not WEEE, but waste to energy, too many abbreviations, into the EU ETS. So this would increase the price of sending material to incineration, so it can change the business case for the material recovery facility. And then, of course, since recycling processes all require energy, but they require it at different levels, energy prices and their fluctuations can also affect the competitiveness of different technologies differently. And then a last important factor, the end product, a recycled ABS, PP, etc., has to compete with its virgin counterpart. So it is also very important and essential to look at how polymer prices, virgin polymer prices, are likely to evolve under maybe increasing ETS prices or also carbon border adjustment mechanism if it includes polymers in the future. So these are some topics from the policy side that are important to take into account when doing an economic assessment of plastic recycling routes. This is our part, and we are still in progress of this study. So if you're interested, don't hesitate to reach out, and also feel free to already put your questions in the chat, and feel free to get in touch with us. And then I hand over to Rucha for the cost of development, the cost of product framework.
Thank you, David. 1 second, trying to take the control. Yes. Perfect. Okay. Hello, everyone. My name is Rucha Kakatkar, and I'm a PhD researcher at Maastricht University in the group of circular plastics. And today I'm going to talk about the cost of product framework that we have developed, also part of INCREASE, and which also incorporates the learnings that we have gained from INCREASE. But before that, I will touch once again on this picture that Teresa showed with the recycling technologies. So when we talk of the recycling cascade, we also can place the recycling technologies in a cascade of themselves. So we have the smaller, lighter green circles coming from physical recycling and the darker green circles coming from chemical recycling. So if we look at mechanical recycling, which gives plastics, as we all know, and it's the shortest route to gaining the final product. But then we go one loop bigger and we go to solvent-based recycling, which then, from my product perspective, gives material at a higher quality, which is important when you talk of product development, but it also gives material at a higher euro price and an environmental cost. And then finally, we go to our chemical routes, which then gives us material of an even higher quality, but coming at an even higher environmental and an economic cost. And that's what we also see, that the output from the chemical process has the maximum number of steps to be undertaken to the final product, as we also saw from the previous speakers. But what we learned from our learnings from INCREASE as the part of work package, which has the business cases, is that from the problem statement of increasing the uptake of recycled plastics into existing products, one has to look at this problem from a business case perspective. So go beyond the raw material prices and look at, for instance, the operational expenditures, to then translate the quality and functionality requirements of your product to the material and then make a choice between the recycling technologies. You also have an effect of the steering framework, which could be external, such as regulations, but it can also be internal, such as corporate targets. We also need to look at time to market, and finally, of course, complete the loop in terms of design for recycling and other end of life considerations. And that brought us to the question on how to choose from a business case perspective between these recyclates coming from the different recycling technologies when we talk of product development. And for this, we developed a methodology or a cost calculation framework, which calculates the cost incurred in the uptake of recyclates into existing products. And for this, we place ourselves going from compounding to production. So the next step from the LCA and LCC that we saw before. And then we really look at available pellets or granulates and converting that into desired products. We look at existing products and not complete product redesign. And then we also focus on electrical and electronic appliances. And in this process, we go beyond the business cases of INCREASE and try to generalize this framework for just products that need plastic parts and are within the electronic sector. And with this, we define different cost categories, so the development cost and production cost, and many different equations behind that to do this cost calculation. So the first cost category on the left is the development cost, which is what we call the cost incurred today. And these costs need to be incurred to make a working prototype to see if a recyclate is working or not. And with this, we have two subcategories, which is the R&D cost and the raw material sourcing cost. And through many equations, we quantify this in a euro per kilo unit. And then we have the production cost, which is the cost incurred tomorrow. So these are recurring costs when the material is launched into production. And that also has two subcategories, and with many equations, we also make it converted into a single euro per kilo unit. So if you look at the first development cost is the R&D cost, and that is basically the quantifying the economic but also the environmental costs of doing multiple trials, depending on different recycling technologies. I want to emphasize here that we are not trying to calculate the absolute total cost of product development, but only trying to quantify the cost categories which will change when your recycling technology changes. Next, we have the raw material sourcing cost, which is basically trying to quantify in euros the effort put in by a full-time employee to find material of a given product requirement or of a given technology. Next, we have the production cost. So the first one there is the process efficiency cost, which includes all costs from maintenance or start and stop losses, downtimes, and so on. And then lastly, we come back to where we started with the story, the raw material price cost. So again, having an economic and environmental factor to it. And from the study, we want two main outcomes. The first is if we compare the development cost with production cost, which is heavier. So is the raw material price still dominating? or how does it look in different scenarios. But then we also want to pile them up and then compare if a product with a virgin material change, how does that compare with a product switch to different recyclates? So this is an ongoing study, but we already have some results from the business as usual scenario. And I will walk you through this graph here. So on the y-axis, we have the total cost, which is the numbers that we have run through the framework. Again, it depends on the hypothetical product scenario that we have run in it. And then on the x-axis, we have different material description of the product. So for instance, MR 25% means that the product is made with 25% mechanical recyclate, 75% virgin material, whereas MR 100% means that it's made fully with mechanically recycled material. And the first thing that we see here is the purple bars dominate, so the production cost dominate. But then we also see in the business as usual scenario that making a product with virgin material is still cheaper than making it with solvent-based pyrolysis and depolymerization. So that's the SBR pyrolysis and the DR. And then when we zoom in at the cost itself, I do recognize that the legends are small, so I will walk you through it. But what we see firstly is the pink bars, and that's the raw material price, the economic raw material price. And the next one, in most cases, what we see is the blue bar, which is the environmental raw material cost. I would like to highlight that these costs are adjusted to recycled content, which means that MR 25% has 25% of its price coming from mechanically recycled material and 75% coming from virgin material. And the reason why the solvent-based and chemical routes look like this is that in our business as usual scenario, these technologies are not scaled up. They are at a low technology readiness level. So we can expect that economic and environmental price to drop as the technology scale up. And we will also look at that next. But how it looks currently is that with increasing recycled content for a given technology, my raw material price is increasing and my environmental raw material cost is decreasing. So for a given technology, they have an opposite effect on my total cost. And what we see for instance, for mechanical recycling is that the savings from environmental raw material cost, so the drop in blue bar, compensates for the increase in raw material price. But we do not see that happening if my slides still move, which they are not. Yes, okay. Okay. So we do not see that happening for the other technologies yet. And that brings me to briefly some takeaways from this, my part of the presentation. So firstly, that we still identify the key cost drivers as the raw material price and the environmental raw material cost. What we also see that in the business as usual scenario, the product price is least for mechanical and still maximum for the solvent-based and the chemical routes. And also in the current scenario, we see this opposite effect of market and environment, where with higher recycled content, we have lower environmental raw material cost and higher raw material price. So this is an ongoing study. What we would do next is firstly do a sensitivity analysis, but also look at the effect of future pathways and conflicts, and to see if there are scenarios where the product with a recyclate could be cheaper than product with virgin material. So for instance, we would see the effect of virgin tax, which will affect the raw material price. As mentioned earlier, we would look at the effect of scaling up of dissolution or solvent-based processes and chemical recycling processes. We would also look at increasing in the carbon pricing, and then also a future renewable energy mix scenario, which will essentially drop all of my environmental cost, and the raw material price will be the only driver. And all of this would hopefully be in a nice paper somewhere early 2026. And that's also it from my side. Maybe Teresa, you can take over because my laptop is completely stuck.
Yes. Thank you very much for your attention. And we are looking forward to your questions. I will stop the recording.